Right, should I start? All right, thank you guys for having me. Excited to talk to you about this work. This is a work about a separation between two important no-go theorems in quantum information. And so I'll start by telling you what these two no-go theorems are: the no-cloning theorem and no-telegraphing. And then I'll give you a proof overview with quantum oracle separation between these two no-go properties. Then I'll go into some complexity theory applications, and specifically between restrictions on quantum witnesses for QMA and QCMA. And finally, I'll talk about some cryptographic applications, specifically this is something called key nonexfiltration. So let me start by telling you what cloning and telegraphing are. So cloning is this process of taking a quantum state and duplicating it into two copies of that same quantum state. So if you have some black box cloner here that takes in one copy and it produces two copies, then we say that it has cloned this quantum state. And the no-cloning theorem, proved by three independent papers back in the 80s, says that a general quantum state cannot be cloned. So what this means specifically is not that there are no quantum states that can be cloned, but just that a general quantum state cannot be cloned. So for instance, so specifically, if this is the set of all collections of quantum states, then there's a subset of them that are clonable. So not every collection is clonable, but there are some that are still clonable. And specifically, one smaller subset of that is a set of classical sets. So for example, if I give you a classical string, some classical data, you can of course duplicate that data. But general quantum states cannot be cloned. So for example, one set of quantum states that cannot be cloned that it falls out here is random. So this is, you can think of this as like a uniformly random quantum state that cannot be cloned. On the other hand, classical strings, say bits, just a sequence of bits, which falls in here, that can be cloned. But there are things that are not classical. For example, the quantum Fourier transform of classical strings, they can also be cloned. Okay, so now telegraphing. So telegraphing is the process of taking a quantum state, converting it by a deconstruction process into a classical message, into a sequence of ones and zeros, and then by a reconstruction process back into a quantum state. And if you can do this and produce the same quantum state on the output that you had on the input, then we say that you telegraphed. This was originally proved by Werner in 1987 as a direct consequence of the no-cloning theorem. He originally called it the no-teleportation theorem. So if you see no teleportation in some cases, this is the same thing. But here we will call it telegraphing to disambiguate it from the the separate process of quantum teleportation. So that's why here we call it telegraphing. But essentially, the no-telegraphing theorem says that a general quantum state cannot be telegraphed, cannot be converted into a classical representation and then back into the same quantum state. And so, like with cloning, this doesn't mean that every quantum state cannot be telegraphed. It means that general quantum states cannot be telegraphed, but there are some states that can be telegraphed, specifically also classical states. Classical states can be telegraphed. And it's not easy, it's not hard to show that any state that can be telegraphed can be cloned. So the set of telegraphable states is a subset of the set of clonable states. And so the way to do this is to do a reduction between telegraphing and cloning. So this reduction goes as follows. It's really simple. Suppose that you can telegraph, which means that you can take a quantum state, convert it, deconstruct it into a classical message, and then reconstruct it back into itself. That means you have this deconstruction and reconstruction process. So what you do is you run the deconstruction once, then you run the reconstruction once and then twice, and then you get two copies of that quantum state on the output. All right. So this shows that telegraphing implies cloning, and it's actually the case in general that it's the other way around. And the reason is because there's a theorem that says that every state that can be perfectly telegraphed or perfectly cloned, all of those collections are just the collections of all orthogonal states. And so really these are the same set. And this is what we say when we mean that information theoretically, telegraphing and cloning are equivalent. Okay, so now, what about efficiency? For computer scientists and complexity theorists, photographers, we like to think about efficiency. How efficient is it to perform these tasks? So let's talk about efficient cloning. Efficient cloning is essentially the same thing, but where the cloner, this black box is required to be a circuit that comes from a uniform family of circuits. And so the set of states that's the collection of states that can be efficiently cloned is a subset, of course, of the set of states that can be cloned in general, right? And same thing with efficient telegraphing. You just require that both the deconstruction circuit and the reconstruction circuit are just uniform families of circuits, polynomial size uniform family of circuits. And so the efficiently telegraphable states are a subset of the efficiently clonable states for the same reason that we said before. If you can telegraph, then you can just run reconstruction twice and clone efficiently. So now the obvious question is, can we do the same thing that we did before? Can we say that, can we characterize the set of states that can be efficiently cloned and the set of states that can be efficiently telegraphed and say that these are equivalent? Or in other words, can we do a reduction between clonability and telegraphability? Can we say that any state that is efficiently clonable is also efficiently telegraphable? And that's the question. Does efficient cloning imply efficient telegraph? And our paper says that no, at least not with respect to query complexity. Specifically, there's no polynomial time black box reduction from cloning to telegraph. The query is to these black boxes. So if you have a black box for cloning, the number of queries that you have to perform in order to do reconstruction is exponential, or at least it's not polynomial. Yeah.
Is there no gap or is it like a
between efficiently clonable and clonable? There is no gap as far as there's no known gap, but we believe that there's a gap. Otherwise, like there's complexity classes that would collapse. I can get back to it later when we talk about complexity classes. Yeah. You're talking about the difference between efficiently clonable and clonable? I don't know that that's that simple, but we can talk about it afterwards if you have an idea for it. I mean, I'd love to figure out, but I don't believe that it's very simple. I think that it would collapse some complexity classes. Mm-hmm. Yeah. Yeah, something that's clonable but not. Yeah, something that's clonable but not efficiently so. Yeah. Yeah, totally. sorry, when I said before, I meant that I would give a separation. It's not a clause. Sorry. Okay. So essentially, our theorem says that efficient cloning does not imply efficient telegraphing. And more specifically, what we say is that there exists a set of quantum states, S, and it's this set psi z, which is labeled by z. Each one has a label z, and quantum oracles relative to which this set F can be efficiently cloned, but it cannot be efficiently telegraphed. And more specifically, it can be perfectly efficiently cloned, probability 1, but it cannot be efficiently telegraphed even with non-negligible probability. And it can be efficiently cloned in the worst case, but not efficiently telegraphed even in the average case. So how do we do this? So first, let me tell you what the scheme is. It starts with a random oracle. And this is just like a black box function from n bits to n bits, and it's just randomly chosen. So randomly chosen function given as a black box, and then we have the following set of states. So it's a set of superpositions over pre-images of a certain image in this of this random oracle. So choose some image of the random oracle. So you choose some output, and just take a uniform superposition over all of the images. So the set of such states is a set of the set S. And note, by the way, that this is a set of orthogonal states. So specifically, it's clonable and telegraphable, though not necessarily efficiently so. So in order to make it clonable efficiently, we give a cloning oracle, and what it does, it just takes every state psi z and bot is the empty register and outputs 2 copies. And you can think of this as the black box. So when we say inner black box separation, what we say is like, if we have a black box for cloning, which is just given as this oracle, if you have this black box, the number of queries what we want to say is the number of queries that it takes to this black box cloner and this random oracle in order to telegraph is inefficient. And so the task that we want to say is that it is impossible using, if not possible efficiently using these 2 oracles, is the task of telegraphing. So we start with some quantum states, psi z, that's from the set, and the label z. You can give the label z, and if you can deconstruct it efficiently to a message C and then reconstruct it back into psi z, then you've telegraphed. So you want to show that this is not possible efficiently. So the first thing we do is rather unintuitive, is we make the deconstruction process, we just consider it to be unbounded. So we just let it, we just don't worry about the efficiency of the deconstruction process. And it would seem that this would make it more difficult to prove the impossibility. But what it does is actually simplifies the format of what we need to prove. And so what we instead, if the deconstruction process is inefficient, then it's just any function. So essentially, we can just replace it with an advice string into the reconstruction process. And so that simplifies what we need to prove. So now all we need to prove is we need to prove that there's no reconstruction process that given some advice string outputs one state. Yeah, so the advice has to be polynomial. Okay, so so this is what we need to prove. We need to prove that you cannot do this reconstruction process using the random oracle and the cloning oracle. But the first step that we do is we just ignore the cloning oracle, forget it exists, and we just show that you cannot reconstruct using just this random oracle. And the way that we do this is we start by first of all ignoring the advice and just saying that if you could reconstruct using the advice, you can also reconstruct without the advice by just guessing the advice. This exponentially decreases your probability of success, but this is okay. Because then what we show is that if you could reconstruct using the advice, you can reconstruct without the advice with potentially smaller probability, but that would give you some size z, and you could do this multiple times to get and then measure each time, measure each output to get a preimage of z, and that gives you a multi-collision, multiple preimages of the same z, and it turns out that it's this gives you some success probability, but there's a lower bound, there's an upper bound on the success probability for doing so, given by Hamoudi and Magniez, that contradicts this. Then in the second step, we bring back the cloning oracle in a limited version where it can only clone size z, only clone the target state. And so we want to say that, like, even if it can clone the target state size z, the z cloning oracle, that doesn't help. And the argument for this is that if it were able to Rani, we can show that changing the cloning oracle on size z, if it has low query on size z, it's undetectable. At least it doesn't give you it gives you a negligible increase in your probability of success. And then finally, we add the full cloning oracle, and we say that if you're able to reconstruct using the full cloning oracle, what we want to say is that we could have also reconstruct using just the one that clones size z. And so what you would want to do is you'd want to just simulate all the cloning on everything else, on all the other states that are not size z. It turns out that that's inefficient. And so what we do is we put in imposter cloning oracles, imposter random oracle and imposter cloning oracle that you keep locally. And what you do is you respond based on these imposter oracles. And what we need, and what we show is that doing so is efficient and is undetectable from seeing the full cloning. Any questions? Go. So what we've shown is that efficient cloning does not imply efficient telegraphing, at least not with respect to, at least not relative to quantum oracle, and specifically in the number of queries and efficiency in the queries. And this is very different from the information theoretic sense, in which cloning and telegraphing are identical, are the same. So this is a surprising result in the efficiency of these two processes. And one thing that's interesting about our proof is that if you remember our proof, what we did is we went through an intermediate stage where we instead of considering the full telegraphing scheme, we considered just this reconstruction process, where we take an device and we output this the quantum state. And it turns out it could be just factored out as its own no-go property that we call reconstruction. And what we really showed in this proof is that efficient cloning does not imply efficient reconstruction. And then it's straightforward to show that efficient telegraphing does not imply efficient reconstruction, because if you can telegraph, specifically you can do both deconstruction and reconstruction, so you can do reconstruction. And so if you combine both of these arrows, it gives you a non-implication between efficient cloning and efficient telegraphing. Any questions about that? And so this reconstruction property, this new reconstruction property is interesting in its own right because of the way that it differs from both cloning and telegraphing. And the specific definition is that it can be state can be reconstructed if if there is some advice for every state in the set, there's some advice that allows you to reconstruct the state efficiently. And the interesting thing is that unlike cloning and telegraphing, this is efficient. This is trivial for inefficient adversaries. So you can always reconstruct inefficiently. So it only appears when considered computational grounds. So specifically, there's no no-go theorem. There's no reconstruction theorem. It's only something that exists with respect to efficient computation. And so my question is to everyone is, are there others? Are there other no-go properties that don't appear until you consider computational assumptions, until you consider efficiency, that in the inefficient world, in the information theoretic world, are either equivalent to cloning and telegraphing, or they're trivial, or they're impossible, but they only become interesting once you consider efficiency. Okay, so now let me move to complexity theory and talk about the applications for complexity theory. And so we start with, everyone probably knows the class NP and the class MA. MA is just like NP, has Merlin and an Arthur. Merlin is unbounded. Arthur is an efficient Turing machine. And Arthur sends a problem instance. Merlin gives back a witness, and then Arthur rejects or accepts. And the difference between MA and NP is just that in MA, Arthur can have random points. And so going from deterministic to random, you can also go from random to quantum, and that's what gives you QMA, or quantum Merlin Arthur. And that's just where the verifier is quantum, and the witness that the prover can send, that Merlin can send, is also quantum. And note that this class is known to be in p-space, contained in p-space. But there's another complexity class that kind of fits in between MA and QMA, and that's QCMA, which is quantum Merlin Arthur, but with classical witnesses. So the only difference is between QMA is that in QMA you have a quantum witness, and QCMA you have a classical witness. But the verifier is still quantum. So let's focus on these two classes, on QCMA and QMA. And note that the only difference between them is the type of witness that you're allowed to have. In QMA, you're allowed to have a quantum state as a witness. In QCMA, you're allowed to have a classical state as a witness. So you can think of QCMA as just a restriction on QMA, restriction on the type of witnesses that can be passed to the verifier. And the difference between them, it's a big open problem in quantum complexity theory of whether QCMA is equal to QMA. And that's the question of whether classical witnesses are as powerful as quantum witnesses for efficient quantum verification. And because the only difference between them is the difference in the witnesses, let's kind of like remove some of the unnecessary part of the picture, and let's just focus on the witnesses, on the classical witnesses versus quantum witnesses. And so because this is a restriction on QMA, this is a restriction on the type of witnesses that can be passed in. What if we put in other restrictions? We talked about some no-go theorems in this talk. What if we restricted based on one of these no-go properties? So for example, the last one we talked about is reconstruction. So what if we require the witnesses? What if we take QMA but require the witnesses to be efficiently reconstructible? And so this gives the class reconstructible QMA, for lack of a better term. And this just is quantum Merlin Arthur with reconstructible witnesses. And so it's easy to see that it's between QCMA and QMA. But what might be less trivial is that it's actually equal to QCMA. So if you have witnesses that are efficiently reconstructible, that means that specifically there's some circuit that reconstructs it from some advice. So you can just give the advice as the classical. Does that make sense? Okay. So since it's equal to QCMA, let's redefine QCMA in terms of reconstructible witnesses. So now QCMA is no longer a class that takes classical witnesses. It's a class that takes quantum witnesses that are reconstructible. And now what about telegraphing? Suppose that we take QMA and restrict the quantum witnesses to be telegraphable states, right? So this gives you telegraphable QMA, which is Marlin Arthur with telegraphable witnesses. And what does that give you? And turns out that this is actually also equal to QCMA. If you can telegraph, if you have a witnesses that is telegraphed, that is telegraphable, you can show that you can actually give it as a reconstructible witness or it's classical witness. And so again, this is actually just equal to QCMA. So let's just move it aside and let's redefine QCMA in terms of telegraphable witness. Okay, so you might be seeing a pattern here. And you might think, well, maybe every no-go restriction on the quantum witnesses will actually collapse it down to QCMA. So let's try it for the last one of these no-go properties that we discussed, clonability. So what if we consider QMA, but with quantum witnesses that are clonable? Now what happens? Does that collapse it down to QCMA? Well, we showed it in this paper that the clonable states are actually, that there exist clonable states that are not telegraphable. Now, this doesn't directly mean that the clonable witnesses are not are more powerful than telegraphable, but it's actually a rather direct consequence of the proof because we give an oracle separation between these two classes based on the same oracles and the same set of states. Essentially saying that this clonable QMA actually, at least relative to quantum oracle, does not collapse down to QCMA. And so you might think, well, in that case, maybe clonable QMA is equal to QMA. Maybe it goes all the way up. Well, we don't have an oracle separation for this, but it would be very surprising if this were the case, because that would mean if these two were equal, that would mean that every problem in QMA has efficiently clonable witnesses. So for example, all local Hamiltonian problems would have ground state witnesses that are efficiently clonable. That would be very surprising. And moreover, the difference between clonable QMA and QMA is exactly where public key quantum money comes in. The public key quantum money crucially relies on this separation between QMA and clonable QMA. So if these two were to be equal, it would be very difficult to see a future for public key quantum money. Yeah. So it's possible that there is an oracle separation out there, and that would be like a strengthening of our paper. Yeah. Yeah. So the proof that we give is relative to a quantum oracle. Maybe there's a way to strengthen it by using just a classical oracle. Yeah. Yes. Yes. That's a good point. So this oracle separation between QCMA and clonable QMA implies an oracle separation between QCMA and QMA. But that's already known. It's already known that there's a classical oracle separation between QCMA and QMA. And so this is a quantum oracle separation, which is slightly weaker, but it's between QCMA and clonable QMA, which is like a stronger in that sense. But yes, because of the existence of a classical oracle separation between these two, maybe there's a classical oracle separation between these two, but we don't know yet. But what we do know is, of course, that if you were able to have an unconditional separation, that would imply a lot of separations between classes that we don't yet know how to do with current techniques. It would be very surprising if you're able to do this, because it would at least imply that P doesn't equal P space, which we don't even know how to do. As in, like, the complexity community doesn't know. Yeah, it just came out a few months ago. Yeah, it's like the randomized one. Yeah, it's kind of weak. Yeah, but it's, yeah, like this. Yeah, I mean, it depends on what you consider. But yeah, it's not the strongest version. Yeah, yeah, that's what we talked about. Yeah. But so this specifically, like presenting it this way, kind of motivates why we really need oracles to separate between these no-go properties, because if we had a standard model separation between clonable sets, clonable sets of states and telegraphable sets of states, that would specifically imply a standard model separation between clonable QMA and QMA, and specifically between QMA and QCMA, between P and P space, or between NP and P space. It implies a lot of separations that are not thought to be possible with current techniques. Okay, so you might ask, like, are there any interesting problems in this new complexity class, clonable QMA? Here is one possibility. It's called the circuit hidden cloning problem, and that's just if you were given a quantum circuit in terms of its gates, it has a polynomial set of gates. Does it clone some hidden state with high fidelity? Or is there or does it act as the identity on all states, all quantum states? And so it's pretty easy to see that this is in clonable QMA, because if there's a witness, if it's a yes instance, that means that this circuit clones some state. So the witness can be just that state, and of course it's clonable by the circuit. And the question is, of course, whether this is not in QCMA. So are these witnesses untelegraphable? And of course, we can't show this without, unconditionally, of course, because that would imply all these complexity class separations. But if it is, and it seems reasonable to conjecture, then this readily gives us a set of states that are efficiently clonable but not efficiently telegraphable. But in this case, it's relative to an assumption rather than to an oracle separation. So finally, the last thing I want to say is I want to give you some cryptographic applications, and that's to the problem of key non-exfiltration. So first, let me give you the problem setup. So we have some classical server that's running lots and lots of queries for its clients. So has some cryptographic key on it. Suppose it's running decryption, encryption queries for all kinds of thousands or millions of clients every moment. And suppose that at some point an adversary, say a worm or a virus, is to take over the server, is to completely control the server, and it wants to take the key and exfiltrate it out to an outside adversary, so that the outside adversary now has the key and can just do the decryption for itself. And so the non-exfiltration property the non-exfiltration problem is how to prevent this. How do we make sure that even if the adversary has gained control of the server, that it still cannot exfiltrate the key to an outside adversary? And so there's a proposal, the existing proposal for how to do this with classical computation due to DiCrescenzo, Lipton, and Wolfish, that essentially just says, this is a rough description, but what it says is to just give a really, really large key. So large, in fact, that if the internal adversary were to try to exfiltrate it, you'd be able to catch them before they were able to exfiltrate the full key, and without the full key, they can just do nothing. And of course, the problem with this is one, you have to have really, really large keys, any kinds of processing, even if you want to back up the key, you want to do all kinds of things, are really inefficient on this really large key. And two, you have to limit the bandwidth with the outside world in order to make sure that they can't exfiltrate the key in time. And these are both problems if you have a server that's running for millions of clients every moment. You don't want to limit the bandwidth. So what could you do if you have a quantum server? So now keep in mind that this is now a quantum server that can run quantum computation, but the task is the same task. It's the same classical task. And specifically, the communication with the outside world is so fast. So they're asking you the same questions, the same classical questions. You're giving the same classical responses. They're saying like, decrypt this for me, encrypt this for me. But now the key locally is quantum. And so if you're able to have the key be a clonable but untelegraphable state, then what you could do is you can clone it as many times as you want locally on the server. For example, in order to parallelize the process, if you have millions of clients every moment, you might want to run them all in parallel on different processes. So you can clone it to run in parallel, and then destroy the extra copies when you don't need them. But if the adversary were to take over the server, they wouldn't be able to exfiltrate the key because the communication with the outside world is classical, so they won't be able to exfiltrate the key by the no-telegraphing theorem. Any questions about this? Okay, so I want to end with this really cute cat who just decided to try to run through our theorem statements. It didn't end quite so well for the cat. So thank you. Inefficiently clonable? Yeah. Oh, that's a good question. They're saying if you take QMA and we restrict the witnesses to be inefficiently clonable, that turns out to be just QMA. Yeah, no, so it's not something that like was looked at before, but it's pretty trivial to see because take any QMA problem has some instance that with some witnesses that are not necessarily clonable. You can convert it to witnesses that are clonable by just attaching the instance problem, like the instance description to the witness. That's just a new witness that allows it to do the same thing. But now it's inefficiently clonable because it's now all the witnesses are now orthogonal. It doesn't. Or yeah, what was the instance? And what? So the problem. So for example.